Hello friends, Rahul Jha welcomes you. Today we are going to talk on topic sodium cooled fast reactor overview and features. So let's start. What is sodium nuclear reactor? A sodium cooled fast reactor SFR is a type of nuclear reactor that uses liquid sodium as a coolant instead of water. These reactors are part of fast neutron reactor family, meaning they use high energy, that is fast neutrons, to sustain the fission change reaction. Unlike traditional thermal reactors that slow neutrons down with moderator. Key features of sodium cooled fast reactors SFRs. Coolant uses liquid nitrogen Na because it has excellent heat transfer properties and high boiling point, that is 880 degrees centigrade at atmospheric pressure, allowing the reactor to operate at high temperatures without high pressure. Sodium does not slow down neutrons, unlike water, making it suitable for fast reactors. Fast neutrons spectrum. Unlike conventional reactors which use thermal neutrons, SFRs use fast neutrons, enabling them to breed more fissile material like plutonium-239 from uranium-238 or burn long-lived nuclear waste. Fuel types can use uranium-plutonium mixed oxide, that is MOX, or metallic fuel, that is uranium-plutonium zirconium alloy. Some designs are breeder reactors producing more fissile fuel than they consume. Design type. Pool type. The reactor core and primary cooling systems are submerged in a large pool of liquid sodium, example BN800 in Russia. Loop type. Sodium circulates through external piping, example Japan's Monju reactors. Advantages. High thermal efficiency due to high operating temperatures. Can reduce nuclear waste by transmuting long-lived actinides. Potential for breeding fuel, extending uranium resources. Challenges. Sodium reacts violently with air and water, requiring inert gas cover systems, requires intermediate heat exchangers to prevent radioactive sodium from contacting water, steam in power generating systems. Historically, some SFRs faced safety issues. Example, sodium leaks in Japan's Monju reactors. Examples of sodium-cooled fast reactors. BN600, BN800 from Russia. Operational commercial fuel reactors, PFBR, India. Prototype fast breeder reactors under commissioning, Monju, Japan. Prototype fast breeder reactors under commissioning, Monju, Japan. Decommissioned due to safety issues. Superphénix, France. Shut down after political and technical challenges. Future prospects. SFR are considered promising for advanced nuclear energy system, including closed fuel cycles and waste reduction. Research continues under programs like Generation 4 International Forum, GIF. Now, we are giving details of SFR technology. Sodium cooled fast reactor, SFR technology. Detailed overview. Sodium cooled fast reactors, SFR, are advanced nuclear reactors designed for efficient energy production, fuel breeding, and nuclear waste reduction. Below is a deep dive into their technology, covering design, operation, and advantages and challenges. Core design and components. Reactor core structure. Fuel assemblies. Typically use MOX, that is mixed oxide, UO2 and PuO2, or metallic fuel, UPU, ZR alloys. No moderator, since it's a fast reactor. High fuel density, 15 to 20% fissile material, 3 to 5% LWRs. Coolant channels. Liquid sodium flows around fuel rods, removing heat efficiently. Control rods, made of boron carbide B4C or hafnium HF, to absorb neutrons and regulate reactivity. Primary cooling system. Liquid sodium Na is used due to high thermal conductivity, 100 times better than water. High boiling point 880 degrees centigrade, allowing operation at low pressure unlike PWRs. Neutron transparency doesn't slow down fast neutron. 2 or 3 cooling loops. Primary sodium loop. Radioactive directly cools the core. Intermediate sodium loop. Non-reactive transfer heat to steam generator. Water steam loop drives the turbine. Pool type versus loop type. Pool type. Integral design. Entire primary system, that is core, pumps, heat exchangers, submerged in a large sodium pool. Example BN800 PFBR. More inherent safety, thermal inertia. Loop type. Modular design. Sodium flows through external pipes. Example Monju, Super Phoenix. Easier maintenance but high risk of leaks. Neutronics and fuel cycle. Fast neutron spectrum. No moderator. Neutrons remain high energy fast. Enables breeding of Pu-239 from U-238 in fertile blankets. Breeding ratio and fuel efficiency. Breeding ratio BR. 1. Produces more fissile Pu-239 than consumed. Example BN800 BR 1.3, PFBR BR 1.05. Can use depleted uranium or nuclear wastes as fuel. Closed fuel cycle. Reprocessing. Spent fuel is chemically treated to extract uranium and plutonium for use. Waste reduction. Transmutes long-lived actinides, example AM, NP, CM, into shorter-lived isotopes. Safety features. Passive safety mechanisms. Negative temperature coefficient. Reactivity decreases if temperature rises. Natural convection cooling. If pump fails, sodium circulates via buoyancy. Sodium-related safety challenges. Chemical reactivity. Sodium reacts explosively with air, forms NaOH plus H2 and water. Explosive H2 release. Requires argon cover gas in sodium pools. Sodium fire prevention. Leak detection system. Fire suppression using powder or nitrogen. Decay heat removal. Passive cooling systems. DRACS. Decay heat removal by natural convection. Guard vessel to contain leaks. Advantages of SFRs. High thermal efficiency, 40 to 45% versus 33% in LWRs due to high operating temperature, that is 500 to 550 degrees centigrade. Fuel sustainability. Can breed plutonium, extending uranium's resources. Waste minimization. Burns long-lived nuclear waste, actinides. Low pressure operation. No risk of high pressure coolant loss, unlike PWRs. Challenges and past issues. Sodium handling difficulties. Corrosion leaks. Example Monju, Japan 1995 sodium leak and fire. High capital cost, more complex than LWRs. Proliferation concerns. Produces weapon grade plutonium. Decommissioning difficulties. Radioactive sodium must be carefully disposed of. Current and future SFR projects. Reactor, country, capacity, status and type. BN800 is from Russia, 880 MWE, operational 2016, pull type. BN1200 from Russia, 1200 MWE planned for 2030s, pool type. PF Bihar, India, 500 MWE under commissioning, pool type. CFR 600, China, 600 MWE under construction, pool type. Estrid, France, 600 MWE cancelled 2019, advanced SFR. Generation 4 goals: improved safety, passive cooling, higher burn-up fuels, longer operation, brittle proliferation resistance. Conclusion: SFRs are promising generation 4 reactor technology from sustainable nuclear energy, offering high efficiency, waste reduction, and fuel breeding. However, sodium chemical reactivity and historical safety issues require advanced engineering solution. Now we'll talk on what are benefits and drawbacks of technology. Sodium-cooled fast reactors. Benefits and drawbacks. Sodium-cooled fast reactors offer significant advantages over conventional nuclear reactors, but also come with technical and safety challenges. Below is a balanced analysis of their pros and cons. Benefits of SFR technology: high energy efficiency, thermal efficiency 40 to 45%, 33% in light water reactors due to high operating temperatures 500 to 550 degrees centigrade. Better electricity output per unit fuel, fuel sustainability and breeding capabilities. Can breed more fissile fuel, plutonium 239 from non-fissile uranium 238. Extends uranium resources by 50 to 100 times compared to traditional reactors. Can use depleted uranium, thorium, or nuclear wastes as fuels. Nuclear waste reduction. Burns long-lived actinides, americium, neptunium, curium from spent fuel, reduces need for long-term geological storage. No high-pressure coolant system. Sodium operates at near atmospheric pressure, unlike PWRs which require 150 plus bar. Eliminates risk of high pressure coolant loss accidents like Fukushima. Fast neutron spectrum advantage. Enables transmutation of nuclear waste, more flexible fuel cycle, MOX, metallic fuel and thorium. Potential for small modular designs. Advanced SFR concepts, example PRISM ARC100, aims for factory-built scalable reactors. Drawbacks and challenges of SFRs. Sodium's chemical reactivity, major safety concern. Explodes on contact with water, air, produces hydrogen gas and sodium hydroxide. Requires argon cover gas system and leak-proof designs. Past incidents: 1995 Monju, Japan, sodium leak and fire, reactor shutdown. Super Phoenix, France, faced political opposition due to sodium issues. Complex and expensive to build. High capital cost than LWRs due to intermediate sodium loop to prevent radioactive sodium water reaction. Special materials, sodium resistant steels. Limited commercial deployment. Less economies of scale. Proliferation risks. Produces weapon grade plutonium Pu-239 as part of fuel cycle. Requires strict safeguards, example IAEA monitoring. Decommissioning challenges. Radioactive sodium must be carefully disposed of, converted to solid NaOH or neutralized. More complex than shutting down water-cooled reactors. Delayed commercialization. Many fast FSR projects, that is Monju, Super Phoenix, Fermi 1, was shut down due to technical political issues. Only Russia, BN 600, 800, and India PFBR have operational large-scale SFRs today. Limited experience and regulatory hurdles. Few countries have deep expertise in sodium fast reactors. Licensing is more stringent due to sodium risks. Comparison with other reactors. Features: sodium fast LWR, lead cooled fast LFR, gas cooled GFR. Coolant for FSFR is liquid sodium, for LWR water, lead or lead bismuth, helium and carbon dioxide. Pressure for SFR 1 atmospheric, LWR high 150 plus, lead cooled fast low, gas cooled fast high 100, approximately 100 bar. Neutron spectrum, fast, thermal, fast and gas cooled fast. Features: SFR sodium fast, LWR lead cooled fast and gas cooled fast GFR. Breeding capability for SFR high, LWR no. Lead cooled fast yes, gas cooled fast yes. Waste burning for SFR excellent, LWR limited, lead cooled fast good, gas cooled fast good. Safety risk for SFR sodium fires, LWR meltdown risk, for lead cooled fast lead solidification, gas cooled fast gas leaks. Future outlook: Russia, India, China are leading in SFR development, BN 1200, PFBR, CFR 600. Generation 4 SFR aims for passive safety and better economics. Alternative coolants: lead molten salt may compete with sodium. Conclusion: SFRs are highly efficient and sustainable, but face cost, safety and political hurdles. If these challenges are managed, they could play a key role in advanced nuclear energy and waste reduction. So this was all about our topic today. Please like and subscribe our channel if you have liked this video. Thank you.